All right. Well, hello class, and welcome back to our lecture 3 or 4 on LMIs in robust and optimal control. So, in the last couple lectures, we talked a little bit about optimization, how everything can be framed as an optimization problem, or should be framed as an optimization problem, perhaps. And that philosophy also applies, of course, to controls, right? It's optimal control. So we have to be optimizing something. And so the first question that we're going to look at is what it is we're going to be optimizing. So what do we want to optimize? And that's not entirely a trivial question. So let's think about the question of what it is we are controlling. So or what we're optimizing. So there's this difference that we have between a system, which is what we are trying to do, right? So we've got maybe a helicopter, for example, and we're trying to make it land safely or quickly and not topple over or something like that. So in that sense, what are we optimizing, right? We're optimizing the system. So, okay, maybe we're optimizing the system. But are we really what does it mean to optimize the system? Well, if you look back at what I said, right? Well, we want to land safely. We want to not topple over. So that's not really the system itself, but what the system does. So maybe performance of the system. Well, okay, what do we mean by performance then? Again, in this optimization framework, we have to very carefully quantify what it is we're looking at. So what is a system? I guess that's a good question. So a system maps inputs, right? We've got inputs here, to something else, which is an output, right? And so the map from the input to the output maybe tells us something about the system. So for example, if there's a bit of wind when we're landing, right, we maybe want to minimize the effect of that wind on our helicopter performance or something like that. Right? So in many ways, what we're trying to optimize usually, right, is some property of the system. So property of the system. Right? Now that's tricky, right? So how do we optimize a property of the system? Well, that's why we have models, right? This for example is Statespace, right? Is a Statespace model, right? And so maybe then we want to, if we have a good model of how the system operates, right? Presumably all the properties of the system are in that model. So maybe there's something about this model that we want to optimize, right? So for example, this model has 4 matrices. 1, 2, 3, 4, right? For things that we can look at, for numbers, if you will. But do they tell us anything about the problem? Do those numbers per se mean anything about how the system is going to perform? Well, maybe not, right? So the question that we need to ask is how can we infer properties of the system from properties of the model? Right, so properties of the model, that's properties of those A, B, C, D matrices, right? So how do those numbers relate to this question of properties of the system? Otherwise, we don't know what we're going to optimize, right? So we need to have some relationship between these A, B, C's, and D's. The A, B, C's, and D's by themselves, right, are fairly meaningless. It's a model, right, parameterized by four numbers. But there are other models, right? We could be using transfer functions to model the system, which would give us an entirely different representation. Or maybe there's some third model out there that we're not too comfortable with, but maybe it's there. And so the model itself, right, is not something we care too much about, except for the fact that we can optimize numbers. Right? We know we've talked a little bit about optimization, how we frame the optimization problem using functions and numbers and LMIs, right? So looking for properties of matrices. So these numbers are very useful because they allow us to pose optimization problems using numbers. Right? Now, okay, but of course we're not really interested in the numbers per se, right? We're interested in optimizing properties. And so the question is, can we pose optimization problems involving those numbers, right, the representation, which yield properties of the system? Okay. And so we have to be very careful, right, because not just any optimization problem involving those numbers, but are solvable only really the convex ones. So what we're going to be looking for, right, then is a way of translating properties of the system to properties of these numbers to a formulation that allows us to optimize over the properties of those numbers, right? Because the properties of the numbers may be fairly complex, eigenvalues and so on and so forth. And so how do we formulate, say, optimization of eigenvalues as a convex optimization problem? Well, that's hard, right? So in this preliminary lecture, we're going to be looking at a very simple case where we're just interested in stability, right? Internal stability up here, right? And we're going to be able to translate that internal stability, interpret it as a property of the map from initial conditions to state, and translate that to properties of numbers, particularly the number A, not focusing on these other numbers, and then show how we can formulate the optimization of that number, the eigenvalues of A, using an LMI, or convex optimization technique. Right. So the first step then, of course, right, is this one here, relating properties of the system to properties of the numbers. And so that's what we're going to be talking about in the first part of this lecture. Right, so getting into the technical parts, right? So we've got our state space model here, right? A, B, C, and D. We have a state, this is the state. An input, this is the input. And an output, which is Y. Now in this lecture, we're going to just ignore these parts of the model, and we're just going to focus on this part right here for the moment. Particularly the relationship between this initial condition and the solution x of t. Solution. And what are the properties of that solution, and how do we interpret those in terms of the matrix A? Yeah. So really what we're starting with is just a very simple system, x dot equals a x of t. And if this was a scalar system, we would already know the answer, right? Well, we would be able to write down what the solution is, right, for an initial condition if this was scalar. Right, we know what the solution is. I mean, if you've taken a preliminary course on differential equations, you almost certainly do, right? If this was just a scalar, then our solution would be e to the, let's make it a scalar for a moment, e to the at, right, times x naught. And we'll make that x naught here. Right, so if it was a scalar, that would be the solution. Well, of course, it's not a scalar because these everything here is a vector. Or x is a vector, u is a vector, y is a vector. And so we have to be a little bit more rigorous, and then things don't work quite as well for vectors as they do for scalars. And again, this, if you've taken 506 or are taking it now, that's the sort of graduate level state space controls course, this should all seem very familiar to you. Okay. So what we're going to do, basically, is see if we can generalize this solution for scalars to a matrix or vector-valued states. Right? And so to do that, right, if x naught is a vector and x is a vector, right, obviously this e to the at must be a matrix in our case. Right? And so the question is there a matrix version of the exponential function? And it turns out there is. Right? So it's a relatively straightforward formulation. The matrix exponential is defined as the infinite series here, right? It goes off to infinity, where we take, there's the initial identity matrix, and we take the sequential powers of the matrix, dividing by these factorial numbers as we get larger and larger, right? So this is actually the definition of the matrix exponential. There's no other way to get the matrix exponential except from the series expansion, right? That's how it's defined. So this is, of course, a straightforward generalization of the scalar version, where we've just replaced the scalar A here with the matrix A. So that's a definition of the matrix exponential. And, of course, it can be shown that this series converges for any matrix A, because those factorial terms, they get very large, and so those quickly overpower any power of the matrix A. So those terms become very small, and the series converges for any matrix. So what are the properties of this matrix exponential? And again, we're not going to get into the matrix exponential theory, or we're not going to actually get much into the theory of state space in this course in general, because we're trying to move quickly. But there are certain properties of the matrix exponential, because we do use it a lot, that you need to know. So many of the properties of the matrix exponential are similar to the scalar, or are inherited from, well, not really inherited from, but are similar to the properties of the scalar exponential. And so we're going to go through the ones that do apply and then the ones that don't apply. So these first three are the ones that do apply. Well, actually, this one doesn't really have an analog in scalar. Right? And the first one is, of course, the zero exponential. If you raise something to a power 0, it's just 1, right? And so that applies to the matrix exponential, and you can see that just because all of these power terms are 0. And so the only power term which is not 0 is the first one, and so the matrix exponential at 0 is identity. All right, so that's an easy one. Another less obvious one, which we use a lot, is this one, which is that the exponential of a transpose of a matrix is equal to the exponential of the matrix transposed. Right? So you can pull that transpose from the matrix to outside the exponential. Right? So it goes from the matrix outside the exponential, and we have these little parentheses here to indicate that. And it's fairly obviously why that's so. It's because if you take the exponential of that transposed matrix and just plug it into all of those powers, right? Then say MT, right, is equal to MT, right? So then we can pull the transpose out of every single term in the entire sequence, and then we get this equal to e to the m transpose. So that's an important property of matrix exponential. And then, of course, the one that we're going to use right now is the most important one for defining solutions, which is the derivative property. So if we multiply the matrix by a scalar, so this is a matrix, and this is a scalar, right? Then if we take the derivative with respect to the scalar, then the matrix pops down out of the exponential. The exponential itself, of course, is left unchanged, right? That's exactly the same term as here. But taking the derivative just pulls one of those a's out of the matrix exponential and puts it in front. And that's it's relatively easy to see, right? If you just take the derivative of the series expansion, right? Well, then this term goes to 0. This term goes to a. And all of these powers, right? This cancels this. Goes to a t, right, and so on and so forth, right? The k cancels the highest exponential, and so we get that every term has an a in front of it, and we can just pull that common term out, and we get what's left over is just the same series expansion, except one sort of delayed by one term. But since it's infinite, it doesn't matter. The rest of the infinite series makes up for it. Right. So we get the matrix exponential times an a function here. So this is not surprising, right? Because the same is true for scalars, right? So these are all the same for scalars. However, there is one property of matrix exponential which is not it is not inherited from the scalar exponential. And that's, well, we know for a scalar, e to the a plus b, right, is e to the a times e to the b. Very important property. We use it all the time in scalars. This is not true for matrices. So e to the m plus n does not equal e to the m times e to the n, unless there is one special case where it does work, and that's where these matrices commute. Now, matrices rarely commute. It's very unusual for a matrix to commute. And so there's only very certain special cases where this property holds. So don't use this property in general, unless you're being very careful. Or we can't use this property. Right, so armed with those three properties of the matrix exponential, it's very easy to find the solution to the normal state space system, x dot equals ax, with initial condition x naught. And in particular, the solution we just give it, it's the same one as for the scalar, except of course this is now the matrix exponential as opposed to the scalar exponential. So there's our matrix exponential. And it's relatively straightforward to prove this is a solution, right? The derivation of that solution is a little bit harder, but the proof that it is in fact a solution, right, is very straightforward, right? All we need to do is, right, propose it and verify that it satisfies these two properties, right? So obviously it satisfies the first property here because e x of 0 equals e to the 0. Right? X naught, when e to the 0, we just proved out on the previous slide, is just identity. And so this is just x naught, right? So it satisfies the first necessary property to be a solution. The second, of course, right, is fairly straightforward as well. D dt e to the a t x naught, right? Well, x naught doesn't have t, and we know that the derivative of e to the at is a e to the at from the, again, property on the previous slide times x naught, which is, of course, our proposed solution here. And so we have a x of t. So our proposed solution satisfies the second property as well. And so since we've satisfied both properties of the solution, and in fact we know the solution is unique in this case, then our proposed solution here is in fact a solution. So we've essentially solved the linear state space systems question with initial conditions x naught. So we actually have an explicit form for the solution, which is actually really quite rare. We can actually generalize that to the input and outputs, but we need a convolution integral, which we're not going to fuss with at the moment. So, okay, we have the representation right here. Representation in terms of A. We have the actual solution. And now what we would like to know is that solution stable, right? What are the properties of A which imply that that solution is stable for any initial condition x naught? So, okay, we said we have a solution. We've written it down, so it seems like it should be fairly straightforward to answer that question. But of course, right, it's not quite the same as the scalar again, right? So what happens to e to the at in particular as, so what's the limit as t goes to infinity of e to the at? Like what happens as time gets large, right? If that goes to 0, then the system's obviously going to be stable. If it goes to infinity, obviously it's going to be unstable. And so, well, which one is it, right? So how do we, in particular, how do we relate that to the properties of A? Right? So unlike the scalar exponential, life is a little bit more complicated in the matrix exponential case. Right? And in particular, we have this sort of limitation that we can't diagonalize matrices. Matrices in general could not be diagonalized using a coordinate transformation. So we have to actually use a fairly sophisticated piece of technology called the Jordan decomposition of the matrix in order to answer this question. And we'll answer it fairly quickly, right? We'll only have like 2 or 3 slides on this. But first, of course, I need to define what the Jordan decomposition is. And I put this this block here because it didn't fit on another slide. So I apologize. It's a little bit premature, but since I have it here, I need to talk about it here. So I need to define what a Jordan block is. So we can't diagonalize matrices, but we can Jordan block diagonalize these matrices. So we want a coordinate transformation such that J equals TAT inverse, where J is as close to being a diagonal as possible. So what do I mean by close to a diagonal? Right. So basically, diagonal in the sense of a Jordan block. Right. So specifically, a Jordan block, right? Jordan block has the form of a diagonal matrix right? So that's a diagonal matrix. And then a single off-diagonal term where it's as close to being 0 as you can hope to get, basically. So basically it's a matrix of all zeros, which we call n. So everything here is 0, which I don't write down, except for one off-diagonal, this off-diagonal right here, which is all 1s. And it's right next to the diagonal, just one space up from it, and it's all 1s, and it doesn't extend over here. These are still all 0s, right? So it's very close to being a diagonal term, right? So an example of a Jordan block would be 3, 3, 3, 1, 1, 0, 0, 0, 0, right? So it's almost diagonal, except for these off-diagonal terms here. Right, so that's what a Jordan block looks like. We don't know what the diagonal elements are, but these off-diagonal elements are all 1. Right. So, okay. Again, that Jordan block was a little bit out of order, but we'll come back to it. So, as we showed when we define the solution to the system, x of t equals e to the at x naught, right? This defines a map from the initial condition to the solution, right? So there's a relationship. If you know the initial condition, you can find the solution exactly. So what are the properties of this system, right? So we have the solution. What property are we interested in? We're interested in the property of stability, of course. So particularly, stability is a property of this input-output map, or initial condition to state map in this case, which says that if for any value of the initial condition, this will go to 0. This thing eventually decays. Okay. So how do we relate that property to the property of this matrix A? Right. So what property of A can we use which allows us to conclude the stability of the system? So in particular, we'll show that there's a certain condition on the eigenvalues of that matrix A, and this actually holds in discrete time as well, except it's slightly different. But the idea is more or less the same, which allows us to take the eigenvalues of A and determine the stability properties of the system. So obviously, in a scalar case, right, x of t equals e to the a t x naught, right, there's no ambiguity. If A is less than 0, so for scalars, A less than 0 is necessary and sufficient for stability. Now, what can we say about the matrix case? Well, of course, it's a little bit more complicated because, right, it's not scalar, but we'll try and get it in a form which kind of looks like a scalar. Right? And that's hard, of course, because we've got these Jordan blocks floating around. Fortunately, however, the non-diagonal part of the Jordan block has this very nice nilpotency property. Specifically, that n that we gave has this property that if you raise it to a high enough power, in particular the size of the matrix itself, it'll eventually disappear, right? So basically those powers of n, right? The first 0 power looks like 0, 1, 0, 1, 0. The second power looks like 0, 0, 1, 0, 0, 0. I'm getting my 0, 0, 0, 0, and then the third power is just 0 everywhere, right? So the effect of that n matrix is to shift the diagonal. Every time you take a power, it shifts that diagonal 1 off until it eventually shifts it off the matrix entirely. So that's a nilpotent matrix. So now we use those properties to tell us something about the properties of the solution. Right? Remember, the solution is x of t equals e to the a t x naught, right? And so we want to look at this particular structure here. So we have this nice useful property that all matrices are Jordan diagonalizable. Not diagonalizable, but Jordan diagonalizable. So in particular, there's a coordinate transformation, a invertible matrix T, an invertible matrix defines a coordinate transformation. Remember, the properties don't depend on the coordinates. This is an important point, right? That a system is stable regardless of how we define that A, right? Because those states, right, they're not unique, right? We could have combinations of those states, which would give us another state representation of the system. But the stability property shouldn't change depending on the representation. And so what this allows us to do is choose a set of states or choose a set of coordinates using this matrix T, right? So x of t, x prime is t x of t, for example, right? Wherein this analysis becomes simpler, right? So specifically, we have this property here, right? And so if we look at x of t equals a x of t, x dot, right? Well, then we can multiply t on both sides. T x of t equals t a x of t. And then we do this substitution where x tilde is tx of t, and then the dynamics become x tilde dot of t equal t a, and then x of t is t inverse of x tilde of t, and so we get t inverse x tilde of t, right? So this is a coordinate transformation which allows us to change our definition of states, and in these states the system becomes just J. Well, actually, I did that backwards. Sorry about that. So actually, right. So, right. If we just define t as t tilde, right, and t tilde is t inverse, right? Then we can do the converse here, right? That t inverse. We'll put the little tildes there, equals J, right? So there's a sort of a converse version of this, which I'm using over here. Right. So this allows us to define a set of states where the dynamics become much simpler, and they become, in fact, almost scalar, right? Almost scalar. So in particular, right, if we look at the solution e to the at, right, what this allows us to do is write this as e to the t inverse, right? And you can show that this actually, we can pull the t's out of the matrix exponential, just get that j there up in the t. Right. So what do we do with that? Well, this term here, right, is almost diagonal. And if it was completely diagonal, right, we'd be done because these would all be scalars and we could determine the properties based on j. Now, of course, I think maybe I didn't mention it, but in the Jordan blocks decomposition of this matrix A, these Jordan blocks, the diagonal terms are given by the eigenvalues. Right? So these are, each of these individual Jordan blocks corresponds to a particular eigenvalue, and then we have the n matrix over here. Right? So we diagonalize A into Jordan blocks, each corresponding to an eigenvalue. Now, if all the eigenvalues are distinct, actually it's already a diagonal matrix and we're done. But in general, the eigenvalues will not be distinct. So okay, now we've got that. So we now expand out e to the j1, or each of these Jordan blocks as a combination of this eigenvalue. This is the eigenvalue times the identity matrix plus the nilpotent matrix n. Now, okay, so clearly if all of these terms go to 0, then we have stability. Right? And so the question becomes, do they? So the next thing we do is we show that you can write, we show that actually that property that you can decompose this addition in the exponent into the matrix sub-exponentials, and that you can do that. I said you couldn't before, but this is one of those very special cases where you can, because in fact a diagonal matrix and this Jordan block, or this nilpotent matrix, actually do commute. This is like the one case where it actually works. And so we can actually do this. We can decompose the matrix exponential into the lambda term, which is easier, and the nilpotent term over here. Right? So if we do that, right, we write down this Jordan block. Right, so this is this Jordan block, right? So we've now got, we rated it to a power t, so we've got we should write in our little t's there, right? This term is here, and this term is over here. So now, well, let's ignore this term because it's obvious, right? These are all scalars, right? So this is, we don't have to even fuss with this, right? These are just scalars. These terms, however, we're going to expand out in the matrix exponential, that series expansion, but we'll use the property that these higher exponents for k, where k is greater than the dimension of the matrix, all go to 0. Right? So all those other terms go to 0. And we're only left with 1, 2, 3 k terms, right? Where k is the dimension of x, right? So actually this says greater than k. That actually is n equals k, right? So sorry about that. The equal to n, right? So hopefully that doesn't cause confusion. So anyway, we have a finite matrix which consists of powers of t and a bunch of exponentials which consist of just the exponent, the scalar exponential. Now, and so when you multiply these terms together, what you get are just a bunch of a matrix of polynomials, right? These all have the term which are polynomial in t, right? Times an exponential, right? And so when you multiply this through, right, you just get e to the lambda I t times a polynomial. So every term in this e to the j I t is every term ij, let's say, is e to the lambda I t times a polynomial in t. Right? And a polynomial is a bunch of monomials added together, so t squared plus 3t cubed, for example. Right? And of course, the important part, right, is that exponentials decay much faster than polynomials increase. So this is actually going to go to infinity. Right, this term here, the polynomial part goes to infinity as t goes to infinity. But this, assuming that if lambda is less than 0, then this term goes to 0 as t goes to infinity. Now you have something going to 0 and something going to infinity, but the point is that exponentials go to 0 much faster than polynomials go to infinity, and so in the end, every term in this solution is going to go to 0 if and only if all the real parts of those lambda i's are 0. You know, I'll just put a little indicator for all I. Okay. So conclusion is that the solution is stable as t goes to infinity, if and only if all the eigenvalues, or specifically the real part of the eigenvalues of A, are less than 0, strictly less than 0. If they're not strictly less than 0, then in theory, right, this polynomial could get large. So again, all matrices have a Jordan decomposition. They don't all have a diagonalization. And so we've now shown that any system, any A, right, is stable, or the system defined by A is stable, if and only if all of the eigenvalues of A have negative real part. So what we've done now is we've taken a property of A, and we've translated that into a property of the system, which is stability. Internal stability, I should say. There are lots of notions of stability. Right now, this is the only one we care about. So this is such an important property of the matrix. Again, this is the property of the matrix that we give it its own name, right? Specifically, a matrix is Hurwitz if the real part of all of the eigenvalues is negative, definite. I'll actually negative, just emphasize definite. Strictly less than 0, right? Even 1 equal to 0, it's not considered stable, right? So that's an important point to make. And then so that's a property of the matrix, properties of the representation. And we've translated it to a property of the system. Okay. Very important step. For discrete time systems, there's a very similar property. Prove it. It's a little bit actually easier to prove in the discrete time system. And we just mention it because we like generating lots of LMIs. And so we'll just, at the end of the lecture, we'll generalize these to discrete time systems as well. So specifically, a discrete time system is this difference equation here, right? So, well, I guess it's not a difference equation, but an update law, which says at each time step you multiply the state by a, and there's only discrete time steps. And it has a similar solution, except it's just the power of a, so it's even actually easier. It's just one of those terms in the matrix exponential. However, for discrete time systems, actually, the property of the system is the same. So essentially, it is the same property of the system, that all the solutions go to 0. But in this discrete time, the property of the representation is very different. So specifically, the property of the system is that the magnitude of all the eigenvalues so it has to be strictly less than 1. So strictly less than 1, right? So that's strictly less than 0 here, and this is strictly less than 1. Okay? So if we draw our complex plane, real and imaginary parts, for continuous time systems, you have stability if you're over here. And for discrete time systems, you want to be in the circle. Right? Those discrete time systems. So very different properties of the matrix A, and it's actually hard to verify in either case, but very different properties leading to the same property of the system. So the representation of the system, discrete or continuous time, actually matters quite a bit in how the properties of the system are derived. Right? So in discrete time, of course, we actually give it a name as well. It's called Schur. I guess people give their names to, I don't know how Mr. Schur got his name attached to discrete time, or how Mr. Hurwitz got his name attached to continuous time, but apparently this matrix property gets named after people. So this is, again, property of the matrix, property of the system. Property of the matrix, property of the system. So again, so we've taken our first step here right now. And now the next step, right, is to relate this property of A to a convex optimization problem. Now you may say, well, actually, I don't need a convex optimization problem. I could just type eigs into MATLAB, and that would give me the answer. But actually, it's not quite that easy, because finding the properties of the eigenvalues of a matrix is actually rather ill-conditioned numerically. And furthermore, if you want to do anything more with this, right, if we want to, say, find a controller which moves the eigenvalues to the left half plane, for example, or do optimal control or anything like that, or stabilize the system, well, then we need to formulate the optimization problem, and so we need to be able to express this as a convex constraint. Is this constraint convex? No, it's not, right? Not convex in A. And this is similarly not convex in A. Oh, sorry, that's the wrong one. This is not convex in A. Right. So when we come back, and here I'm going to just, it seems like a natural spot for a break, I will talk about how to formulate the convex optimization problem. Well, actually, I'll take a next step, and yeah, well, we'll talk about, yes, it's how to formulate the convex optimization problem.